Angela Partita, and I will be presenting the introduction portion of our report. Guillermo will be presenting the data, and Sabrina will be closing with our conclusion. For our analysis, we wanted to look into baseball hitting averages. We wanted to know if the number of strikeouts by a player affect the overall batting average for that player. The reason that we picked this topic was that we all all of our team members like baseball, and since we are currently in baseball season, we wanted to look into these batting averages since they largely drive decisions made in baseball. Again, a little background on baseball statistics. They are essential to big decisions made in Major League Baseball, and they provide numbers that have a great effect on whether a player is traded, drafted, most importantly, when these athletes' skills are incorporated during major games. For our report, we selected our explanatory variable to be the strikeout percentages per player. And our response variable is the batting average for the same baseball player. In our calculations, we are trying to see if the number of strikeouts affect a player's overall batting average. Here is a look at our data. The data that we collected is from 45 players with their batting average and their strikeout average, respectively. Line equation, which is y is equal to negative 0.4336, x plus 0.3259. And now interpreting the data, the slope of line regression is negative 0.4336, which means that the strikeout average as the strikeout average increases by 1, the batting average of the player goes down by 0.4336. And the y-intercept means that if there are no strikeouts, the player's batting average is 0.3257. We do not view this y-intercept as a reasonable interpretation of the batting average, because there are other factors that go into a player's batting average, such as the amount of hits that they have, if they're walked, and other things like that.
I'm going to be presenting the data. So as you can see here on the screen, we calculated for the correlation coefficient R using the Excel. We were able to find that our R was equal to 0.621. We determined that since the value is closer to 1 than it is to 0, there was a moderate correlation. And then we assumed that the correlation was a negative because the slope of the line in our scatter plot was going down. There is a negative moderate linear correlation between the strikeout average and the batting average. This means that the batting average is affected by the player's strikeout average. Then we wanted to determine the coefficient of R squared, and we got R squared is equal to 0.386. We determined that our model could be 38.6% sure that the variation in Y is explained by the variation in X. So we must assume that 61.4% is not covered in our model. There is a weak variation, but you can still use the model to predict the variation. So we assume that if we know a player's strikeout average, we can use our model to determine a player's batting average and be correct about 38.6% of the time. Our regression model does show that there is a linear correlation. You're going to see it on the next slide here. That there is correlation, and as we previously calculated, there is going to be a 38.6% sure that there is a relationship And although our model is weak, we can still use it to estimate a person's batting average based on their strikeout average. Here's our scatter plot. So the blue dots represent what was given in the original raw data, and then the orange dots and the line represents the predicted batting average. So as we can see here, it's going down to the right, so we assumed there was a negative correlation. Again, we use the raw data of 45 players batting average, and we use it to graph it against their striking average. Again, that represents the blue dots, and then we plotted it against the predicted batting average using the regression line equation. This is our residual plot. We use this calculating by subtracting the actual batting average minus the predicted batting average, and we see that there is a little bit of variance. We could see that there's not really any outliers that will affect it, the linear equation, so we predicted that the line does fit our data.
Hi everyone! Sabrina here with the summary of our group's statistical findings and overall conclusion of our interpreted data. So with regards to our findings, there are quite a few bullet points to discuss. Firstly, we discovered a negative correlation coefficient of R equals negative 0.6213, which signified a moderate negative relationship between our X and Y variables. This means that when the strikeout percentage, our X variable, increased, it had a moderate negative impact on the overall batting average, our Y variable. We also found a linear regression model with the equation y equals negative 0.4336x plus 0.3257. So based on this result, we concluded that the model had a downward slope and an uninterpretable y value, with the scope that fell outside the bounds of the regression model. Because of the limited role the y variable played in this equation, our group was also able to conclude that the explanatory variable could be used as a good predictor for the response variable. Moving on to our next point. We also needed to discover the potential of variation in our model, so we then went on to solve for the coefficient of determination, which we calculated had a value of r squared equals 0.3860. Because this value is greater than 0, positive, but less than 1, we concluded that this coefficient of determination reflected a weak correlation between the variables, but it could still be used to predict variation within our model. We were also required to perform a t-test, and after performing a hypothesis test to check the correlation between our explanatory and response variables, our group concluded that because our p-value of 0.000005 was less than the significance level used for the prediction test, in this case 0.01, we had to reject our initial hypothesis and state that there was a linear correlation between striking percentages and batting averages. Lastly, in order to further confirm our findings, we also ran diagnostics on the linear regression model via the usage of residual plots, and we found the distribution to be fairly random. There was a constant variance with a scatter around 0, and there were no influential outliers, all of which are necessary conditions for using the linear model. This finding strengthened the value of our weak correlation coefficient and also allowed for us to conclude that the use of the linear model was indeed appropriate. Moving on to the last slide. After combining all of our statistical evidence, we concluded that there is a moderate negative linear relationship between strikeout percentages and batting averages. Additionally, our group now has a better understanding of the role statistics plays in the decision-making processes of baseball experts, and that without statistics, baseball would not be what it is today. Thanks for tuning into our presentation, and we appreciate your time.